Welcome, learners. We are commencing a focused, a very high-intensity technical revision session. This is the deep dive. Today, we're executing a comprehensive review of B vehicle technology and maintenance management.
And I am your senior technical instructor. My role here is to ensure we achieve, well, absolute concept clarity. We're here to structure your knowledge for exam-ready recall.
Our objective is precise. A full chapter-level revision in just this one session. We're going to move beyond simple definitions to really understand the mechanics, the physics.
And the digital logic. You have to understand the logic driving modern transport.
Exactly. The standard is high. We expect you to grasp not just the what, but the how, and critically, the why.
That's right, because that depth is what you'll need for any application-based questions.
We're following a strict top-down structure, divided into 4 key sectors. First, Sector 1, Fundamentals. We'll be dissecting internal combustion engines, cycle logic, and the critical differences between spark and compression ignition.
Then Sector 2 will cover systems. We'll look at modern fuel delivery, so MPFI and CRDI and things like turbocharging.
Sector 3 is all about dynamics and safety. We'll cover steering, tire technology, especially for military applications, and the physics behind systems like ABS and airbags.
And we'll finish with Sector 4, future trends. So we'll break down hybrid systems, the EV landscape, and of course, the SAE levels of autonomous driving.
Let's engage immediately. Conceptual Layer 1. Engine fundamentals.
Ready.
Okay, we have to start with a core definition. In the context of B vehicles, what is the precise technical definition of an internal combustion engine, or IC, that a learner would need for the exam?
Right. An internal combustion engine is, at its heart, a heat engine. The defining feature, the thing you have to remember, is where the combustion happens. The burning of fuel with an oxidizer, which is usually air, it occurs inside a confined combustion chamber. That's the key, internal.
And how does that generate work? What's the mechanism?
So that combustion creates high temperature and high pressure gases. These gases, they have to expand.
Right.
And that expansion applies a direct force to the engine's movable parts, typically pistons or maybe turbine blades. That force moves the component, and that generates useful mechanical energy.
It's critical, then, for learners to distinguish this from an external combustion engine.
Absolutely. Think of a classic steam engine. In that system, the working fluid, the steam, is heated by a source outside the engine. The fire is external. In an ICE, the fire is internal. That is the fundamental classification.
Okay. Now, within the ICE family, we primarily use 2 categories in the armed forces: spark ignition, SI, and compression ignition, CI. Let's start with the spark ignition engine, the petrol engine.
In an SI engine, the process starts with a mixture. Air and fuel are mixed before they even enter the cylinder. In older systems, this was a carburetor. Now it's fuel injection. The goal is to create what's called a homogeneous charge.
And there's a specific ratio for that charge, one that learners absolutely must memorize: the stoichiometric ratio.
Yes, that ratio is approximately 15:1. 15 parts air to 1 part petrol by mass. That is the perfect chemical ratio for complete combustion. If you deviate from that too much, the engine just won't perform well.
The second defining feature, then, is how it's ignited.
Exactly. The SI engine has a relatively low compression ratio. We're talking maybe 5:1 up to 9:1. So during the compression stroke, the mixture is squeezed, but it only reaches, say, 60 to 80 degrees Celsius.
Which isn't hot enough to ignite on its own.
Not even close. So it needs an external energy source. And that source is an electric spark from the spark plug. That's what kicks off the combustion.
Okay, so now let's contrast that directly with the compression ignition engine, the CI, or diesel platform. The difference starts right at the induction stroke, doesn't it?
It does. It's a fundamental difference. In a CI engine, you are not inducting a fuel mixture. During that first suction stroke, the engine draws in only air, just pure air.
And taking the fuel out of that initial equation changes everything for the compression phase.
It allows you to be much, much more aggressive. Because there's no fuel in there to pre-ignite or knock, we can compress that air to a much higher ratio, typically 15:1, maybe even up to 22:1.
We're compressing it to what, around 40 bar?
About 40 bar, yes. Compare that to the 8 to 14 bar in a petrol engine. It's a huge difference.
And basic thermodynamics tells us that compressing a gas that much generates a lot of heat.
A massive amount of heat. The air temperature spikes to approximately 550 degrees Celsius. That number, 550 degrees, is critical. That heat is the ignition source.
So there's no spark plug. How does combustion actually start?
Right at the top of the piston stroke, fuel is injected directly into that pocket of superheated air. The heat of the compressed air is so intense that the fuel droplets vaporize and ignite spontaneously.
Autoignition.
Exactly. The air itself provides the ignition energy.
And learners should be thinking about the implications of this design. Higher thermal efficiency, for one.
Yes, significantly. Up to 40% thermal efficiency, whereas a petrol engine is closer to 25%. You're just extracting more work from the fuel. But there's a trade-off.
The structural cost.
The structural cost. To withstand 40 bar of pressure cycle after cycle, the engine construction has to be heavier, much more robust, and that's why diesel engines are perfect for heavy-duty applications where torque and efficiency matter more than weight.
Let's move to the mechanical cycles, the four-stroke versus the two-stroke. Most of our standard vehicles operate on the four-stroke principle. Can you walk us through that sequence?
Okay, the four-stroke cycle. It requires 4 distinct piston strokes. So that's 2 complete revolutions of the crankshaft just to get 1 power stroke.
Let's break them down. Stroke 1, induction.
Inlet valve opens, exhaust valve is closed, the piston moves down, creating a partial vacuum.
Which sucks the charge in.
Right, it's drawn into the cylinder.
Stroke 2, compression.
Now both valves are shut, the piston moves up, squeezing that charge into the combustion chamber.
Then stroke 3, the big one. Combustion, the working stroke.
Ignition occurs. The expanding gases force the piston down with incredible power. And learners, please note this. This is the only stroke in the entire cycle that actually produces power.
And finally, stroke 4, exhaust.
The exhaust valve opens, the piston travels back up, and in doing so, it pushes all the spent, burnt gases out of the cylinder. So the key metric to remember is that ratio. 1 power stroke for every 2 crankshaft revolutions.
Okay, so how does the two-stroke cycle manage to do all of that so much faster?
Well, the two-stroke engine completes that whole process. Induction, compression, combustion, exhaust in a single revolution of the crankshaft. Just 2 strokes of the piston.
And the architecture is different. It usually doesn't have valves in the same way.
That's right. Instead of traditional valves, it uses ports. These are just openings drilled into the cylinder wall. You have an intake port, an exhaust port, and a transfer port. The piston itself acts as a sliding valve, covering and uncovering these ports as it moves.
Which means processes are happening at the same time.
Exactly. So on the upstroke, as the piston is compressing the charge above it, it's also creating a vacuum in the crankcase below, drawing in the next charge. Then on the downstroke, the power stroke, as the piston moves down, it first uncovers the exhaust port to let the old gases out, and then the transfer port to let the fresh charge in.
So what's the operational trade-off here?
You get more power for a given size, and it's much lighter because it's firing on every revolution. The downside is that the process of scavenging, clearing out the old gas, and bringing in the new is not very efficient. So you get poor fuel economy, higher pollution, and generally more wear and tear.
Okay, that covers the fundamentals. Let's move to conceptual layer 2, modern fuel and induction systems. We're really talking about the shift from mechanical guesswork to electronic precision, starting with petrol. Multi-point fuel injection, or MPFI.
MPFI is what replaced the carburetor. It uses electronic injectors, and the key word here is multi-point. These injectors are mounted in the intake manifold, and there's one dedicated injector for each cylinder. The whole thing is managed by an electronic control unit, the ECU.
The ECU is the brain of the operation. How does it know how much fuel to deliver?
It's constantly reading data from a network of sensors. It's looking at air mass, engine speed, coolant temperature, throttle position, all of it. Based on that data, it calculates the precise injection drive time.
So the exact amount of time the injector nozzle stays open.
Down to the millisecond, exactly.
We need to clarify the 2 main control modes, open loop and closed loop.
Right. Open loop is basically the default mode when the engine is cold. The sensors, especially the oxygen sensor in the exhaust, aren't up to their operating temperature yet. So the ECU ignores their feedback and just runs on a pre-programmed map, delivering a richer mixture to keep the engine running smoothly while it warms up.
And then it switches to closed loop.
Once everything's warm, yes.
Yes.
It enters closed loop. The ECU starts listening to the oxygen sensor. It uses that feedback from the exhaust to constantly fine-tune the air-fuel ratio in real time.
Why is that fine-tuning so important?
It's all about the catalytic converter. The converter needs a very specific chemical balance in the exhaust gases to do its job properly and reduce emissions. Closed-loop control maintains that balance.
So, learners, for the exam, the operational advantages of MPFI are critical. It ensures uniform fuel distribution.
Right. Every cylinder gets the same amount.
It eliminates vapor lock, which was a problem in hot weather for carbureted engines. And for our operations, this is key. It provides automatic altitude compensation.
That is a huge point. As you go up into the mountains, the air gets thinner, right? The air density drops. A mechanical system would keep delivering the same amount of fuel, so it would run rich and lose power.
But MPFI?
MPFI's air mass sensor detects the lower air density and automatically cuts back the fuel to maintain that perfect 15-to-1 ratio.
Okay, now for the diesel equivalent. Common rail, direct injection, CRDI.
CRDI is the gold standard for modern diesels. In older mechanical systems, a pump had to create high pressure for each injection event, and that pressure was tied to the engine's RPM. CRDI completely decouples pressure generation from the injection timing.
Explain what the common rail itself is.
It's basically a high-pressure fuel line or tube that's shared by all the injectors. A separate high-pressure pump keeps this rail filled with fuel at a massive constant pressure. We're talking around 29,000 psi. And that pressure stays high regardless of what the engine speed is.
What's the benefit of having that constant massive pressure on tap?
Precision. It allows the electronic injectors to fire with incredible speed and accuracy. The ECU can command multiple tiny injections per combustion cycle. You can have a small pilot injection to quiet the engine down, then the main injection, then even a post-injection to help with emissions. It results in a quieter, cleaner, and much more efficient engine.
Let's talk about forcing more air in. Forced induction, superchargers versus turbochargers. The goal is the same for both, right? Increase volumetric efficiency.
Correct. You're physically forcing more air, more oxygen into the cylinder than the engine could suck in on its own. More air means you can burn more fuel, and that means more power.
Let's define the supercharger first.
A supercharger is an air compressor that is mechanically driven by the engine itself. It's connected directly to the crankshaft by a belt or a gear or a chain.
So what are the pros and cons?
The big advantage is that the response is instant. There's no lag. As soon as the engine speeds up, the supercharger speeds up. The disadvantage is what we call parasitic load. The engine has to use some of its own power just to spin the compressor, which hurts overall efficiency.
Now, contrast that with the turbocharger.
A turbocharger is much cleverer. It uses waste energy. It's essentially two fans on a common shaft. One fan, the turbine, is placed in the exhaust stream. The hot, expanding exhaust gases, which would normally just be wasted.
Spin the turbine.
They spin the turbine at incredible speed. And that turbine is connected to the other fan, the compressor, which is in the intake path. So it's using wasted exhaust energy to force fresh air into the engine.
So it's recycling energy.
Precisely. It improves the whole system's efficiency. The only small downside is that you have to wait for the exhaust pressure to build up to spin the turbine, which can cause a slight delay in response. We call that turbo lag.
And there's a vital safety component in turbo systems, the wastegate.
Yes, the wastegate is a pressure relief valve. If the exhaust pressure gets too high, which could make the turbo spin too fast and create too much boost, the wastegate opens and lets some of that exhaust gas bypass the turbine. It's there to prevent the engine from destroying itself.
Before we leave this sector, a quick word on CNG, compressed natural gas.
CNG is used as a cleaner burning alternative to petrol. It's stored in high-pressure cylinders, around 200 bar. So a key component is the pressure regulator, which has to step that pressure way down to near atmospheric levels before it can go into the engine.
And what are the maintenance benefits of running on CNG?
It's actually better for engine life. Petrol is a liquid, a solvent. When it's sprayed into the cylinder, it can wash the lubricating oil film off the cylinder walls. CNG is a dry gas, so it doesn't do that. It preserves the lubrication. Plus, it has a very high octane number, around 130, so it resists knock and burns very cleanly.
All right, that brings us to conceptual layer 3, vehicle dynamics. We'll focus on steering and tire technology.
Steering systems have really evolved. They've always been about balancing driver effort with vehicle stability. We started with purely manual steering. Very reliable, simple, but it causes a lot of driver fatigue, especially in heavy vehicles.
Which led to hydraulic power steering, or HPS.
Right. HPS uses a pump, driven by the engine's belt, to pressurize hydraulic fluid. And that pressure does most of the work for you. But standard HPS has a flaw.
It gives you the same amount of assistance all the time.
Exactly. Which can make the steering feel too light and sensitive at high speeds. It's a stability risk.
And the solution to that was electronic variable orifice steering, or EVO.
EVO adds some intelligence. It uses a solenoid valve that can restrict the flow of the hydraulic fluid as the vehicle's speed increases. So, Less assistance at high speed gives you a stiffer, more stable feel on the highway. And then at low speeds, like when you're parking, the valve opens up for maximum assistance.
And now the modern standard is electrical power assisted steering, EPAS.
EPAS gets rid of the hydraulics completely. It uses an electric motor right on the steering column or rack. The ECU reads data from torque and speed sensors and tells the motor exactly how much help to give.
The efficiency gain must be significant.
It is. A hydraulic pump is always spinning, always drawing power from the engine. An EPAS motor only draws power when you're actually turning the wheel. That saves fuel, and it also means no hydraulic fluid to leak or maintain.
Let's shift to tires. The two key concepts are radial construction and tubeless design.
So, radial tires have their internal ply cords running radially at 90 degrees to the direction of travel. This construction gives you better grip, better fuel efficiency compared to the older bias ply design. But the real safety innovation is the tubeless design.
How does a tubeless tire hold air without a tube?
It has a special inner liner made of what's called halogenated butyl rubber that's bonded directly to the inside of the tire. This liner is impermeable to air.
And the failure mode is completely different.
Completely. With a tube, if you get a puncture, the high-pressure air bursts out and you get an instantaneous deflation, a blowout. With a tubeless tire, if a nail goes in, that soft butyl liner tends to press in and seal around the nail. So instead of a blowout, you get a slow leak, which gives the driver time to maintain control and pull over safely.
And in the armed forces, we take that further with run-flat technology and CTIS.
Run-flat tires have incredibly stiff, reinforced sidewalls. They're strong enough to support the vehicle's weight even with zero air pressure, allowing a vehicle to get out of a kill zone. And CTIS is the central tire inflation system. It lets the driver adjust the tire pressure from inside the cabin on the move.
Explain the tactical use of CTIS.
It's all about adapting to the terrain. If you're on soft sand or mud, the driver lowers the pressure. This makes the tire flatten out, creating a bigger footprint, which gives you more traction.
And then on a hard road,
you pump the pressure back up. A harder tire has less rolling resistance, runs cooler, and is much more efficient and stable at high speeds.
This leads us to conceptual layer 4, active and passive safety systems. Let's start with a passive system, the airbag.
The airbag is a classic passive safety system. Its job is to manage momentum. In a crash, the vehicle stops almost instantly, but because of inertia, the occupants keep moving forward at the original speed. The airbag's job is to bring that person to a stop more slowly and safely.
And the mechanism is purely chemical.
Correct. It's not compressed air waiting in a tank. When the sensors detect a severe impact, something like hitting a wall at 10 to 15 miles per hour, it triggers an inflator. This starts a very rapid chemical reaction between sodium azide and potassium nitrate.
And that reaction creates a gas.
It creates a massive volume of harmless nitrogen gas incredibly quickly. The whole bag inflates in about 125th of a second, faster than you can blink. And it's designed with vents, so it immediately starts deflating as the occupant makes contact, providing a soft cushion rather than a hard bounce.
Okay, now for active safety, the anti-lock braking system, or ABS.
ABS is designed to solve one specific problem, a locked skidding wheel. When a wheel locks up under braking, it's no longer rolling, it's just sliding. And a sliding tire has very little grip and absolutely no steering control.
So how does ABS prevent that?
The ECU constantly watches the speed of each wheel. If it sees one wheel slowing down much faster than the others, a sign that it's about to lock, it rapidly modulates the brake pressure to that specific wheel. It'll reduce, hold, and then increase the pressure in a very fast cycle. You feel it as a pulsing in the brake pedal.
What's the main operational benefit? Most people think it's about stopping shorter.
And on some surfaces that's true, but the primary benefit, the reason it was invented, is maintaining steering control. By keeping the wheels rotating right at the threshold of locking, ABS allows you to brake as hard as possible and steer around an obstacle at the same time.
Electronic stability control, ESC, is the next step up.
Yes, ESC is basically an evolution of ABS. It uses all the same wheel speed sensors, but it adds two crucial new ones: a steering wheel angle sensor and a gyroscopic sensor, or yaw rate sensor.
So it's comparing what the driver wants to do with what the car is actually doing.
Precisely. The steering angle sensor tells the ECU where the driver is trying to go. The gyro tells it how the car is actually rotating or turning. If there's a mismatch, if the car is turning more than the driver wants, which is oversteer, or less, which is understeer,
then the ESC steps in.
It steps in and applies the brake to one single specific wheel to create a turning force that nudges the vehicle back onto the driver's intended line. It's an incredible system.
Which brings us to our final section, conceptual layer 5, future propulsion and autonomy. We're seeing a big shift towards hybridization.
A hybrid vehicle, by definition, uses two distinct power sources, usually an internal combustion engine and an electric motor. There are two main ways to connect them, parallel and series.
Let's define the parallel hybrid first.
In a parallel setup, both the engine and the electric motor are physically connected to the transmission. This means they can power the wheels either on their own or for maximum acceleration they can work together at the same time.
And the series hybrid is different.
Very different. In a series hybrid, the internal combustion engine has absolutely no mechanical connection to the wheels, none. Its only job is to turn a generator.
So it's basically an onboard power plant.
That's the perfect way to describe it. The engine generates electricity, which can either charge the battery or go directly to the electric motor. It's the electric motor and only the electric motor that drives the wheels.
What are the tactical advantages of that series architecture?
A few big ones. First, you can run the engine at its single most efficient RPM all the time, which saves a lot of fuel. Second, it enables silent watch or silent drive modes, where you can move or observe using only the battery, which is great for stealth. And third, you can use the vehicle as a mobile power generator for a command post.
Now let's clarify the different types of electric vehicles.
We basically have AEVs and PHEVs. An AEV is an all-electric vehicle. It runs 100% on battery power, zero emissions, zero noise, but you are limited by range, maybe 125 to 160 kilometers for a standard vehicle.
And the PHEV.
That's the plug-in hybrid electric vehicle. Think of it as a bridge technology. It has a much bigger battery than a normal hybrid, so it can go maybe 6 to 40 miles on electricity alone, but it still has a combustion engine that kicks in for longer journeys. The key feature is that you can plug it into the grid to charge that bigger battery.
Finally, let's talk about autonomous vehicles using the SAE levels of autonomy.
Right, it's a scale from 0 to 5. Level 0 is easy, no automation. The driver does everything.
Level 1.
Level 1 is driver assistance. The system can help with either steering or speed, but not both at the same time. Think of basic cruise control.
Level 2.
Level 2 is partial automation. The system can control both steering and speed. But, and this is the crucial part, the human driver must be supervising at all times. Eyes on the road.
Level 3 is where the responsibility starts to shift.
It's a huge shift. Level 3 is conditional automation. The system is now monitoring the environment. The driver can, in theory, look away. However, the driver has to be ready to take back control the instant the system asks them to. This handover is a major challenge.
And the highest levels.
Level 4 is high automation. The vehicle can drive itself without any human input, but only within a specific geofenced area or under certain conditions. And if something goes wrong, it can safely pull itself over. Level 5 is full automation. The vehicle can do everything a human driver can, anywhere, under any conditions. No steering wheel needed.
And what's the technology that enables all of this? Connectivity, V2X.
Vehicle-to-everything communication. It's all built on things like 5G. You have V2V, vehicle-to-vehicle, so cars can warn each other about braking. You have V2I, vehicle-to-infrastructure, so a car can talk to a traffic light. And you even have V2G, vehicle-to-grid, where an EV can act as a temporary storage battery for the power grid.
And internally, even the health monitoring is changing.
Right, the sensors are turning inward. We now have steering wheels that can measure your heart rate. If the driver has a medical emergency and becomes incapacitated, the vehicle can detect that and bring itself to a safe stop.
Learners, that concludes our structural overview. We have moved all the way from the basic thermodynamics of an engine to the digital complexity of a fully autonomous vehicle.
So, to summarize for your revision, on engines, remember the key difference. Spark ignition is low compression, external spark. Compression ignition is high compression, using that 550-degree air for auto ignition.
Systems.
MPFI and CRDI are about electronic precision winning out over mechanical approximation.
And on safety.
ABS and airbags are just clever engineering solutions to the basic laws of physics, friction and momentum.
And on the future.
The vehicle is no longer just a vehicle. It's becoming a connected, hybrid thinking node in a much larger digital world.
We really encourage you to review the comparison tables in your source text, specifically the ones contrasting SI versus CI engines and parallel versus series hybrids. Those are very likely to be exam topics.
Focus on the mechanisms. If you can explain how a system works, you can figure out the why and the what when you're under pressure.
This concludes our technical revision session. Study hard.
And stay safe. End of session.